All right, this is the video for the session 4 homework for kinematics equations. All right, so starting off with problem 1, we have a ball rolls downhill with a constant acceleration of 4 meters per second squared. So I see meters per second squared. Let me get the right color here, and I'm just going to go ahead and let's do that color there. So acceleration is 4 meters per second squared. You can put down the units, you don't have to. Definitely don't put the units in the equation. If it started from rest indicates that this is going to start at 0 meters per second. Its velocity, so I'm looking for velocity, at the end of 3 seconds is blank. So moving on to, so I've got my 3 givens, I've got my unknown, I don't care about delta x. Since I don't care about delta x, the equation I'm going to use is v equals at plus v naught. And I'm going to go ahead and substitute in of v equals a times t plus v naught. Sorry, this is problem 1. And now I'm going to go ahead and solve it. So v equals 12 plus 0. So v equals 12 meters per second. And that is problem 1. So for problem 2, ball rolls downhill with a constant velocity of 4 meters per second squared. It starts from rest. Its velocity after 3 meters. Meters means that's distance. I'm still looking for velocity. In this case, time is the variable I neither have nor care about. Since time is the variable I do not have or care about, I'm going to pick this equation there. So I'm going to say v squared equals v naught squared plus 2 times a times delta x. So now I'm going to go ahead and solve. V squared equals 0 squared, which is 0, plus 2 times 4 times 3. 2 times 4 is going to give you 8, times 3 is going to give you 24. So that's v squared equals 24. And to get rid of the squared, I'm going to go ahead and take the square root. And the square root of 24 is 4.9 meters per second. Now, there is a decision here because remember, when you take a square root, you have to do a plus or minus. In this case, we started at rest and have a positive acceleration. So I can just go ahead and leave that as positive 4.9 meters per second. If I started at 0 and had a negative acceleration, then it would be negative. It just depends on what the sign of your acceleration is in that case. All right, problem 3. Ball rolls downhill with a constant acceleration of 4 meters per second squared. It starts, if it started from rest, its displacement at the end of 3 seconds is, so in this case, v is the variable I do not care about. So I'm going to pick the equation that does not have v, and I'm going to substitute in delta x equals v naught t plus 1/2 a t squared. So to solve this, delta x equals 0 because 3 times 0 is 0, plus 1/2 4 times 9 because that's 3 squared. So delta x equals 1/2 times 4 is going to give you 2. 2 times 9 gives you 18 meters. All right, problem number 4. Ball rolls downhill with a constant velocity of 4 meters per second squared. If it started from rest, how long will it take to travel 20 meters? In this case, v is the variable I do not have or care about. So I'll select that variable equation there. So delta x is equal to v naught times t plus 1/2 a t squared. So to solve this, I've got 20 equals 0, because 0 times anything is 0. 1/2 times 4 is 2. So I've got 20 equals 2t squared. I'm going to divide both sides by 2. So 10 equals t squared. I will take the square root of both sides to get rid of the squared, and I get square root of 10, which is 3.16 seconds is equal to time. Problem 5. A ball rolls downhill with a constant speed or constant acceleration of 4 meters per second squared. If it started from rest, how long will it take to reach a speed of 20 meters per second? In this case, the variable I do not have or care about is delta x. So I'm going to pick the equation without delta x. So then I'm going to substitute in that v equals a times t plus v naught. So that's 20 equals 4t, because adding by 0, I can just drop it, divide by both sides by 4, and I get that 5 seconds is equal to time. For problem 6. A uniformly constantly accelerated body increases in velocity from 10 meters per second to 25 meters per second in 3 seconds. Its displacement is, its acceleration is what? So in this case, delta x is the variable that I do not want and do not care about. So v equals a times t plus v naught. So 3a plus t, I'm going to go ahead and, plus 10. I'm going to go ahead and subtract over the 10 from both sides. So I get 15 equals 3a, divide the 3 from both sides, and I get 5 meters per second squared is equal to the acceleration. Now, I'm going to go ahead and do something a little different for this problem and write this over here. And that's so that I can go ahead and erase this and start problem 7, because for problem 7, you had to have done problem 8 correctly. So we start with all the same variables because it now says what is the displacement. Well, in all of these equations, you have V naught and A. You must have V naught and A to solve any of these problems. So we needed to do problem 6 before you could do problem 7. If I just gave you problem 7, you would have to say, well, all of these require acceleration and decide to solve for acceleration first. I believe there's an example of this down later. So now it's not what variable I don't care about, because I have all of them except for the one that I now want to know. So pick any equation that has delta x in it. In this case, I could pick either of the other two. Given the choice, I'm going to choose this equation because it's already set equal to what I had, but I will at the end show you that either approach works. So delta x equals v naught times t plus 1/2 a, which we already found from previous, t squared. So delta x equals 30, that's the 10 times 3, plus 3 squared is 9, times 5 is 45, times 1/2 is going to be 22.5, so delta x is equal to 52.5 meters. Now, I said I could have used equation 3, and I could. I could do 25 squared equals 10 squared plus 2 times 5 times delta x, because 25 squared would give me 625. 10 squared would give me 100. 2 times 5 gives me 10 delta x. So 625 minus 100 is 525 equals 10 delta x. Divide both sides by 10, and 525 divided by 10 gives you 52.5 meters, exactly the same as we found over there. Either equation works. Problem 8. A car is moving at 18 meters per second and slows and is brought to rest, which implies it comes to a stop, so V is 0, at a constant rate in 5 seconds. How far did it travel? Okay, I'm going to do something interesting here. I'm going to do problem 8 and 9. So we are looking for how far did it travel in 3 seconds, because here's the problem. I cannot solve problem 8 without first solving problem 9, because notice in this case, acceleration is the variable we do not care about. However, this equation has acceleration, this equation has acceleration, and this equation has acceleration. You must know acceleration and initial velocity to solve for anything else. So if you are not given one of those, you must solve for it first and then the variable you care about. In this case, you need to do 9 before you do 8. I do not need to ask 9. You might be asked to just figure that out on your own without the hint. But you have to know acceleration and initial velocity. If you know neither acceleration nor initial velocity, you cannot solve these problems at all. So in this case, I'm going to first find acceleration, meaning I temporarily do not care about delta x, in which case I'm going to choose this equation here. So final velocity equals acceleration times time plus initial velocity. So that's 0 equals 3a plus 18. I'm going to subtract 18 over from both sides. That gives me negative 18 equals 3a. Negative 18 divided by 3 gives me negative 6 meters per second squared. Now, this should make sense because you are slowing down. Now, do not get caught by thinking that just because you're slowing down, your acceleration must be negative. Slowing down means your velocity and your acceleration are opposites. Okay, so in this case, we started with a positive initial velocity. That means we have to have a negative acceleration if we're slowing down. If we had a negative velocity and we're slowing down, we would need a positive acceleration. They're simply opposites of one another. Now, to solve for problem 8 now, to go back and actually solve for the original thing we cared about, now you can pick any equation here that has delta x in it. Again, I'm going to choose to use the equation that has delta x. I'm simply going to write it under here. So delta x equals v naught times t plus 1/2 a, which we now know is negative 6, t squared. And you simply plug this in. So delta x equals 18 times 3 is going to be, let's see, 20 times 3 would be 60, minus 6 is going to be 54. 3 squared is 9, times negative 6 is going to be, times negative 3 squared is 9 times negative 3, because you got the half times negative 6. So negative 3 times 9 is going to be negative 27. And so delta x is 54 minus 27, which is going to be 50, 47, 27 meters. I'm going to double check that because it's too late for me to be doing mental math. Yeah, 27 meters. All right, so for problem 10, we're going to come back to problem 10. We're also going to come back to problem 11. Problem 12. Once fired, a bullet accelerates at 6.8 times 10 to the fourth meters per second squared. So 6.8 times 10 to the fourth meters per second squared through a rifle barrel. If the barrel is 0.8 meters long, how long does it take before the bullet leaves the barrel? So again, not stated, but a bullet before it's shot is not moving. So your initial velocity is 0. We want time. We don't care about v. So I'm going to come over here to the equation that does not have final velocity and say delta x equals v naught t plus 1/2 a. Just for the sake of this, I'm going to, let's see, that would be then followed by 3 zeros, 68,000 meters per second squared. You can leave it in scientific notation if you want, t squared. So 0.8 equals 0, because 0 times anything is 0. Half of 68,000 is going to be 34,000 t squared. There's really no reason to convert the scientific notation because this is going to be a really tiny number anyway. Because we're going to divide over the 34,000. And we get 0.8 divided by 34,000 is a very tiny number, which is 2.35 times 10 to the negative fifth equals t squared. I'm going to go ahead and take the square root of both sides to get rid of the squared. And when I do that, I get that the time is 0.0049. I round to 2 decimal places, seconds. Please don't forget your units. For problem 13, bullet once fired from a rifle, so it starts at rest because, well, it's not moving if it hasn't been shot yet. 6.8 times 10 to the fourth is its acceleration, meters per second squared. If the barrel is 0.8 meters long, then how fast was the bullet going as it left the barrel? I do not care about time. I will use my equation that does not have time. So v squared equals v naught squared plus 2 times a times delta x. So v squared equals 13.6 times 10 to the fourth times 0.8. I just multiplied the 2 in because I could. Not that it matters because I've got to multiply everything together now. So v squared equals a very large number. What would that even be? 1,088,000. And then we will take the square root of that to get rid of the squared off the v. And that is 1,043.07 meters per second. Again, plus or minus. In this case, I choose the velocity will be positive. Problem 14. I'll come back to that later because that's one of the other challenging problems. Uh, 15. A bunny travels 500 meters at a constant speed. Okay, so again, you could go directly to, this is the only equation we have for constant velocity, but let's say forget that. How do you do this just using the kinematics equations and not anything extra? Easy enough. Travels at 500 meters per second. at a constant speed of 8 meters per second. How long does it take the bunny to travel that distance? Now, we know one other thing. If you are traveling at a constant speed of anything, your acceleration must be 0, because acceleration is a change in velocity. If you're not changing velocity, you can't have an acceleration. So the equation we don't care, or with the variable we don't care about here, is v. So I'm going to choose this equation right here. So delta x equals v. Whoops, sorry, if I'm going to substitute in, I should do it correctly. Delta x, which is 500, equals v naught times t plus 1/2 0 t squared. In this case, because you're multiplying by 0, all you're left with is 500 equals 8t. Divide both sides by 8. And t would be some number. 62.5 seconds. So a little over a minute for that bunny. Problem 16. A car moving at a uniform speed of 25 meters per second. Again, uniform speed means 0 acceleration. Circular track with a radius of 100 meters. Okay, so this is a problem where things start getting a little different, where you can't just rely on this exact method here, because makes its way around a circular track with a radius of 100 meters. What is the distance around the track? Well, if I have a track with a radius of 100 meters, then what I need to do is the circumference of a circle is equal to 2 times pi times r. So it's equal to 2 times pi times r. And 2 times 3.14 gives you 6.28 times 100 gives you 628 meters plus change, but I'm happy ignoring that. How long does it take the car to go around the track once? Again, you can treat your acceleration as 0. That means you're looking for time, and your total distance traveled is 628 meters. You don't care about velocity, so this is your equation, but I'm going to save us the time and say this term goes away because your acceleration is 0 and multiplying anything by 0 is 0. So you're going 628 meters around the track at a velocity of 25 meters per second. What is your time? So I'm not even going to bother rewriting this. You're just dividing 628, your answer from part A, by 25. 628 divided by 25 gives you 25.12, I'm sorry, seconds. Problem 17. A car is at rest and then accelerates at 5 meters per second squared for 10 seconds. So first up, how far does it go? How far means distance. In this case, we don't care about velocity, so I will select this equation here. So delta x equals v naught t plus 1/2 a t squared. Yes, I didn't substitute in the t there. I just realized I made that mistake. However, since it's multiplied by 0, that whole term goes away and is pointless anyway. 10 squared is 100. 5 times 100 is 500 times half is 250 meters. Now for part B, having found this is 250 meters, it says, what is its final speed? At this point, we don't want this equation. We want any equation that has v in it. The easiest one is this here. You could solve for this. It doesn't matter. So v equals a times t plus v naught. V is 50 meters per second. Problem 18. A car starts at rest and reaches a speed of 50 meters per second after traveling 100 meters. How long does it take and what is its acceleration? This is another case where you must do B first because we have no equation that doesn't have A. So right now I'm going to go for A and choose to ignore time. If I'm ignoring time, that means I'm using this equation here. V squared equals V naught squared plus 2 times A times delta X. 50 squared is going to be 250, I believe. Let me double check that. Yeah, right, 2,500. 0 plus 2 times 100 is 200. So since this 0 term goes away because adding 0 doesn't do anything, I can just divide the 200 from both sides, and I get an acceleration of 12.5 meters per second squared. Now that I know this, I can go back and now solve for time. Again, any equation here works. I'm going to choose to solve for this one right here. Now, you can use the second equation. However, and I'm going to switch to red for this, I'm going to provide a cautionary tale on why you might not want to do the second equation. Because if you do the second equation, that's 100 equals, actually you can do the second equation, that's fine. But if we didn't have an initial velocity, that would be a quadratic equation. So, and we'll see that later on where sometimes you want to avoid the second equation to avoid the quadratic. But I'm going to choose to do V equals A times T plus V naught. I can ignore the 0 and just divide over the 12.5. And 50 divided by 12.5 is 4 meters per second. Or sorry, 4 seconds. I'm solving for time here. Problem 19. A car goes from 36 meters per second to 20 meters per second in 4 seconds. What is its acceleration? And then we're going to ask how far did it travel. So first up is the acceleration. I don't care about delta x yet, so I'm just going to go ahead and do v final equals v naught times t. Nope. I screwed all that up. Let's try this one more time. So I'm using v final equals at plus v naught. I'm going to go ahead and subtract over the 36. So 20 minus 36 gives me negative 16. A times 4, divide both sides by the 4, and I get an acceleration of negative 4 meters per second squared. Now that I have that, I can use anything to solve for delta x, but I'm going to go ahead and use the equation set equal to delta x. So delta x equals v naught times t plus 1/2 a times t squared. So delta x, 36 times 4 is going to be 60, 120, 144. Again, too late for me to be doing mental math. Yeah, 144. Minus, because I'm multiplying by a negative here, negative 4 times half is going to be negative 2 times 4 squared is going to be 36, because 16 times 2 is 36. Yeah. And then 144 minus 36 is going to give me 108 meters. Problem 20. Okay, so this is where I'm going to go back and do. I'm going to go back and do problems 10, 11, 14, and 20 and 21 because these are slightly more complicated problems. So let's go back and do 10. A car starts at a green light and accelerates at 6 meters per second squared. A truck passes through the same light at the same time going in the same direction at a constant rate of 24 meters per second. How far will the car have to travel before it catches up to the truck? So this is a case where I have two objects, so I need to set up two equations. So first up is going to be just the green car. So I'm going to go ahead and do the green car in green. As horrible as these colors will look together. So the green car, sorry, it starts at a green light. So we'll just do the normal color for this. Okay, so for the car, it has an initial velocity of 0. It doesn't actually say it's 0, but that's what we're gonna have to assume for this. This is just a poorly written question, I apologize. I don't know how I haven't fixed this yet. And accelerates at 6 meters per second squared. We don't know time and we don't know delta x. Okay. Um, all right. For the truck, which I will do in, we'll say white. It has an initial velocity of 24 meters per second. It continues going that speed. It has no acceleration because it's at a constant speed. Okay, so here's what we can do. What we can do is we can set up for the truck delta x equals vt. So delta x, the distance it travels, equals its velocity times time. We can also set up for the car delta x equals, we're going to use equation 2 here, v naught t, so that whole term goes away because v naught is 0, plus 1/2 a t squared. Because what we can do is say the 1/2, sorry, let me simplify this equation first. So for the car, we can say delta x equals 3t squared. So what we can do is say, because both of these are set equal to delta x, we can put them together and say 24t equals 3t squared, and then solve for t. So to do that, I'm going to divide both sides by t. So that cancels out, that cancels there, and then I have 24 equals 3t, divide both sides by 3, and t is equal to 8 seconds. Now the question says, how long will it take for the car to catch up to the truck? At 8 seconds, they will both have traveled the same distance. They both started at the same point. Therefore, that is how long the car has taken to catch up to the truck. For problem 11, is the same kind of thing where we're going to go ahead and set up a set for the car. I'm switching colors this time apparently, and we'll set up a set for the truck. All right, so for the car, again, car starts at green light and accelerates at 6 meters per second squared. Have to assume that it's at rest. Okay, so this is the exact same setup as 11, so I should have actually done these as the same problem, where here we have a initial velocity of 24, and here is an acceleration of 0. So again, if I set up the equation for the truck, I can use essentially this equation right here and say delta x is equal to v naught t plus 0, because if your acceleration 0, this whole term is going to become 0. Then I can set up the car, which is going to be delta x equals v naught t plus 1/2 a t squared. So delta x equals 1/2, 1/2 times 6 is going to be 3 t squared. Now, what the difference is, before I set these two equations equal to each other right now, I can get plus, I can go away. But because I was looking for time, here I want displacement. So what I'm going to do is I'm going to solve each of these equations for displacement. So, or sorry, for time. So I'm going to do delta x over 24 equals t. And I'm going to go ahead and do divide the 3 over and take the square root. So the square root of delta x over 3 is equal to t, because now I can set these two equal to each other, where I can say, because they're, both set equal to time, so I can say square root delta x over 3 is equal to delta x over 24. And now I can go ahead and cross multiply. All right, well, first thing I'm going to do is I'm going to go ahead and square both sides. So I'm going to get delta x over 3 equals delta x squared over whatever 24 squared gives you, 576. Now I'll cross multiply. Well, I can make my life even easier. I can divide both sides by a delta x. So this is just 1 and that's delta x. And now I can cross multiply. So 576 equals 3 delta x. Divide both sides by 3, and delta x is equal to 192 meters. There's an easier way I could have done this had I thought to do problem 10 and 11 as the same problem. We know it took 8 seconds. So you could have said, okay, for this equation here, how far would you go in 8 seconds? And it's 24 times t. So 24 times 8 gets you 192. That's the easier way to do this problem, is, think ahead. All right, problem, let's see, the next one I did was 14. So again, we're gonna have to set up two trains. So we'll have train A, we'll have train B, and we'll have to set up two sets of equations for them. Let me trace over that B with white. All right, so train A. Two trains are accidentally put on the same track, so they're on head-on collision course. Train A is moving at 28 meters per second and can decelerate or slow down at -4 meters per second squared. Train B is moving at 30 meters per second. Now I'm going to do something and I'll explain it in a second, and can decelerate at 5 meters per second squared. When the trains are 190 meters apart, they spot each other and immediately apply their brakes. How long do they collide? Okay. So here's what I did, and we might not need this bottom. I can't remember, so we'll see. I'll come back to this if I need to explain this. You actually won't need that. That's fine. Anyway, what you're doing is, so it said 28 and 30, -4 and -5, but the two trains are going at each other. So if this is 28, this has to be negative 30 because they're going towards each other. And if you're slowing down, your velocity and your acceleration need to be opposite signs. So that's why I switched the signs for train B. All right, so I'm going to do the same thing. Yeah, we're going to do the same thing we did before. So we're just going to go ahead and set this equal to delta x. So let's ignore that I wrote this. I don't think we need it. So I'm going to go ahead and set up for train A first. So we've got delta x equals 28 times t plus 1/2 a t squared. And then for all right, I'm going to do 14 and 20 together because they're essentially the same problem. You're just switching out the numbers. So you're going to do the same thing with a train A and a train B. So train A we know is traveling at, for 14, is traveling at 28 meters per second. They are trying to come to a stop. The acceleration is -4 meters per second squared, and we don't know the time. For train B, which I'll do in white, and again, 20 is the exact same thing, just swap out the numbers, that's it. Now, I'm gonna do something here. That's 30, it's coming to a stop, and 5 meters per second squared. Now, if you notice, I flipped the signs. And the reason is because one train is going this way at 30 meters per second, and the other train is going this way at 28 meters per second. One's going right, one's going left. They have to have opposite signs. And because they're both slowing down, their acceleration has to be opposite of velocity. Train A is going to the right, it's a positive velocity, it's slowing down, it must have a negative acceleration. Train B is going to the left, it must have a negative velocity, and it's slowing down, so it has to have a positive acceleration. All right, so then what I'm going to do is I'm going to use this equation right here. Or actually, I'm going to go ahead and use this equation here. I don't want to mess with time if I don't have to. So what I'm going to do is I'm going to set up 0 squared equals 28 squared plus 2 times a times delta x. And I'm going to solve for the distance this train takes to stop. So that's going to be 0 equals 28 squared is 784 minus 8 delta x. So I can subtract over the 784 equals -8 delta x. So divide both sides by -8. And delta x is equal to, for train A, 98 meters. So now we can do the exact same thing for train B. 0 squared equals the -30 squared plus 2 times A times delta x. 30 squared is going to be 900. I didn't actually have to change the signs here. I did because I was going to do it another way, but it's all good. All right, so subtract the 900. 10 delta x, divide both sides by 10, and this is -90 meters. So it travels 90 meters to the left. So one train takes 90 meters to stop, the other train takes 98 meters to stop. If you add those together, you get 188 meters, or 2 meters short of their stopping distance. So no, they would not crash. Problem 20 is doing the exact same problem, just with different numbers. And you already have the answer for that. Finally, we have problem 21. Another case where we have a train A and a train B. So for train A, it's moving at 40 meters per second as it passes train B on a parallel track, and it doesn't say anything about accelerating. So that's all we assume it is traveling at a constant speed. B starts at rest and accelerates at 5 meters per second squared. How long does it take for the train to catch up to train B, and how far do they travel during this time? So again, this is very similar to problems 10 and 11, where we are going to set up two equations. So I'm going to go ahead and use this equation right here. So for train B, delta x equals v naught t. Again, that whole term becomes 0 times 1/2 a t squared. So delta x is equal to 2.5 t squared. And for train A, it's delta x equals vt plus 1/2 at squared, which is going to be 0 because your acceleration is 0. If a is 0, then everything it's multiplied by is 0, and that whole term goes away. So this one I've got delta x equals 40t. I am then going to set these two equations equal to one another and go ahead and solve. So I can divide both sides by a t. So I get 40 equals 2.5 t. T is equal to 40 divided by 2.5, which is 16 seconds. Now I can save myself some time, and instead of rewriting these to be equal to t, setting the t's equal and solving for delta x, for part B, I could just go back and say, well, delta x equals 40 times 16. So therefore, they travel 640 meters.